Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I would like to introduce our keynote speaker, Doug Berger. Many of you know him already. He's Director of Client and Cloud Applications. I think that's the name of the organization in Microsoft Research Technology side. And in his previous life, he has been a professor at UT Austin. And I've been working on computer architectures and silicon scaling. And a lot of his recent work and previous and recent works are about low power computing. So it'll be a pleasure and to introduce Doug for his keynote.
Okay, gee, thank you for the introduction. So I guess this is, by your taxonomy, this is a teaser keynote, right? And it's a low energy, low power session, and the faculty summit is pretty grueling for everyone with the amount of amazing people. So maybe this will be a low energy keynote since it's coming up at the end of the week. So what I set out to do is to give a computer architect's perspective. I know there are people like David and Ross who intersect with, or Ross intersects with computer architecture here, and a lot of you are working in circuits and very, very low power devices and energy scavenging and sensors. So I thought I'd give a computer architect's perspective on what's coming with silicon scaling and what I think some of the directions are forward to get programmable systems that will be able to run at much lower power. Okay, so I think we all know that we're facing a bunch of challenges. Eric Chung, came up with this really nice slide showing a large impact event that the end of CMOS scaling with nothing really sitting behind it to replace the levels of progress and scaling that we've gotten used to is a pretty major event. And we're now in that end game, and we don't know exactly where because we don't know how it will all play out. But we've all become used to a 50-year exponential reducing energy per op, reducing cost per transistor, allowing for higher performance designs. And so now that we're in the midst of this twilight and this transition, we're going to start seeing ripple effects that have progressively larger and larger effects on the industry. And so in the low power space, I think the implications are pretty profound because we've come to rely on consistent improvements in energy efficiency per operation. And if you don't get those for free anymore, you have to do a lot more work to get them. And I think that's really the effect that this community is going to see. So Shekhar shared this slide with me a number of years ago, and it's interesting because at the time, this was around 2012, we were saying, okay, we know how to scale up to about 2014 to 16 nanometers, and then Shekhar said, then things get really, really tough after that. And what's interesting is that if you look at this is the CMOS roadmap, so this is your year, obviously, and then technology node in nanometers and the number of billions of transistors you can put on a chip. We were expecting to get to 11 nanometers around 2016, and what we're seeing is that it's so hard that the cadence is starting to slow, right? So in some sense, Moore's law is already cracking, and that it was supposed to be generating a regular cadence, and that the pace of that cadence has shifted, sometimes slower, sometimes faster over the decades. But we're now starting to see this. Somewhere in here is where we run into economic limits to scaling, if not physical limits. And I personally believe that it'll be economics that bring this thing to a screeching halt, as opposed to, we're not capable of manufacturing smaller devices even with the lithographies they have. The question is, do we get enough gains to economically justify going forward? And I think increasingly the answer is no. So I have two other slides on that just to give some, or three other slides just to give some context. So, and I think most people know this pretty well. I thought that the visual of it was pretty striking, that here we have year roughly corresponding to process node, and this chart is even a couple of years old. And then on the y-axis here, we have number of companies building leading edge fabs. So who is at the leading edge for CMOS process manufacturing? And obviously people have been dropping out, and so we're down to about 5 That's 5 is certainly plenty, but it's because of the costs. And that has had, the costs in particular, has had a number of effects. So the number of ASIC starts each generation has been dropping fairly precipitously because the costs to do a high-end ASIC go up. So if you're going to build a large aggressive ASIC, the barrier to entry now is $100 to $200 million to do something aggressive. And that's driven a lot of the startups that are doing chips out of business. That's not to say there are no chip startups. A lot of people are doing designs on trailing edge designs, older designs, or doing fabless designs, coming up with an idea and then evaluating on FPGA and then trying to find a partner who will put in the money to take it to production. But the number of companies doing high-end chips has gotten so low that the venture community doesn't even really track it anymore. Although there are still, it's not a zero number. But the ASIC costs just have been going up and up and up, and that's in addition to the fab cost of the equipment. Okay, so now if you look at why people drop out, there's a really interesting ratio, which is the revenue you get from silicon to the cost of the fab. Okay, and what we can see is that over history, there's this dropout zone with a range of that ratio, and when companies enter that zone, they tend to drop out. Okay, again, it's not 100% correlation because, as you can see, Global Foundries has been kind of kicking underneath that zone for some time. They're more of a consortium. They have national sovereign wealth funds investing. So, and there's a lot of reasons to keep them alive. So, but they're certainly economically a lot more challenged. If they were an independent business without any subsidies, they'd be really, really challenged. And then you can see that TSMC has been skirting along the upper edge of that zone for a while. They also make a lot of their money off of older fabs. And then, we have more subsidies. But the two that are really way above the zone are Samsung and Intel. But you can certainly see that they're on an intercept course. And so I think the natural conclusion to draw is that, in a generation or two, it'll just get harder and harder, and there won't be more than 2 companies at the fabs. And that's even assuming that they can make the gains economic. Okay, and this is the chart that really floored me, which is, if you look, and this is for TSMC, but if you look at the cost per transistor, the argument is that it has largely flattened, and in fact, it's even projected to go up a little bit to the 14 or 16 nanometer node. Okay, and that's really what turns this whole thing around, because we've had exponential drops in the cost per transistor for many decades. And so you can double the number of transistors on a part, and it costs about the same. Okay, and the cost both to build the fabs and the wafers and the double patterning, the number of design rules, the yields, it's all gotten so hard that it's actually driving the costs up. I've talked about this with the CEOs of both Altera and Xilinx. As you might imagine, they're particularly interested in that trend. Both of them have basically said, yeah, this is true. This is what we're seeing, and right now we're making up for it with architecture and tweaking our designs to get more logic with less cost. But we're not seeing just a raw transistor cost drop. Okay, and obviously tweaking the architecture, you can't just keep doing that and getting big gains year after year if you stay with the same model. Okay, so that's a really big deal. Now, I've talked to other people, and in the industry, and they've said, well, the cost at 16 is going to drop a little. TSMC is basically building for 16 nanometers, 20 nanometer area transistors with 16 nanometer like performance, because they're going to Tri-Gate or FinFETs. And so they may resume. We don't know what will happen with Intel. Intel may squeeze another generation or 2 out. And again, you hear mixed things. But we're clearly at a point where the easy stuff is over, and individual companies may fall off more quickly. But we're not seeing the big drops and the easy drops, even with a lot of, it was hard doing it here, but it's gotten really hard. I guess one other comment is that the way I see this playing out at the end is that we're going to overshoot by 1 generation, because you don't know a priori if you'll be able to bring the cost down, because once you start deploying them and you start manufacturing at scale, you're able to tune the process, you keep improving things, you improved your yields, and the cost curves come down. The really scary thing is that I think what's going to happen is we're going to move into some node, we're all going to be counting on it, we're all going to be very excited for the number of floating point units and the number of, the energy performance and the level of integration we can do. And with the products roadmaps are specified and people have built the ASICs and they're designing them and we're waiting for them to come. And then at some point, the companies, the fab companies will say, we can't afford this. And they'll either drive the prices up or they'll roll back to the previous generation. And that will be like in 2004 when Intel canceled its high frequency part and made a hard right-hand turn. I mean, it will send shockwaves through the industry. So I do think we'll end up, there's just too much momentum for them just to stop beforehand, because it's the business model. They'll push ahead, they'll hope that they can bring the costs down, and then we'll say, whoops, and then we won't know that until we're well into it. Okay, so how does this play out? And this will be my last slide on the kind of market implications. Then we'll start talking more about technical things. So the semiconductor companies are going to have to change business models to a large part. And so Intel, I think, will become a foundry. They've already started. Intel manufacturing other people's designs 10 years ago was unusual, to say the least. They're now partnering with several FPGA companies, and as many of you know, Altera will be manufacturing their high-end parts on Intel's 14-nanometer process starting next year. Personally, I think the FPGA companies will have to become service companies. They won't be able to drive large volumes of silicon, people upgrading to the next parts, so they're going to have to start building designs and SoCs and building solutions, which will be a huge cultural change for them. We'll start to see licensing models like ARM has proliferate. So you'll build some IP and you'll try to license it to lots of people. Obviously, not a very large number of players will be successful there. We'll start to see rapid ASIC services proliferate because of the need for energy efficiency and specialization. People will want to build ASICs, but right now it's too slow, it's too long, it's too expensive. And so people will provide lots of IP blocks, even more than today in the ARM ecosystem. You'll be able to cobble them together through well-defined interfaces and bang them out much more quickly than today. Right now we're moving in the opposite direction, where it takes longer to build an ASIC than it did at the leading edge, a generation ago. We need to turn that around and make it shorter. Over time, if the process stays stable, the tools will mature. And I expect much more industrial activity around those sorts of services. But when you do that, in all of these business models, your margins are much lower. And so we'll see the semiconductor industry as a whole become a lot smaller. That's not to say by parts, we may still see many more parts being sold, but it'll be a less profitable business. And so a lot of these new models that people will move to will be much less profitable than today. The other thing we'll see is that the industry will verticalize a lot as the silicon becomes more of a commodity. So all the people at the bottom will start running up the stack, and we're already starting to see that consolidation with acquisitions in the fab space and the tool space. And so they'll be running up as the big players will be running down into more specialized silicon, and there'll be a lot of tension on that interface, and it's going to be really interesting to see that play out. And when everyone's trying to run up the stack and down the stack, it's going to be very disruptive to business models, especially for the fabless semis, the AMDs and the NVIDIAs and the FPGA companies and others, because they have to move to new business models, and you can't do that on a dime. But this hard stop will be a surprise when it happens. So we'll see a lot of churn there. And then some of you may have seen the slide before that I've used a few times in talks. But if you look at the way the industry used to look, we had a much more horizontal ecosystem. And this is well known. It's becoming increasingly well known that we had device manufacturers. Apple, of course, had their own OS and devices. Microsoft had some productivity apps, but then people would build apps on top of it. But then in the hardware space, things were largely stratified. And you had the same thing in the cloud, where people were building servers and chips. And then Google, of course, started building their own data centers fairly early on. But then what's happened over the last some number of years, oops, my animation didn't make it, so I'll just keep clicking until it does. 5, 6, 7, 8, 9, 10. There we go. 11. How did that happen? Somehow I got 10 dummy animations put in there. We've seen the industry start to verticalize on a number of integrated players. And I think we expect this trend to continue. And so recently over the last 4 or 5 years, you've seen these companies start to push much, much more aggressively down into first devices and then chips, and on the top end, building their own data centers, but then building their own servers, and then increasingly, and we're starting to see there's all these rumors about people building their own chips for the data centers. And of course, I didn't draw the fabs on top of that. So I think what you're going to see as this trend continues and accelerates with the changes we see in technology scaling is these pillars will eventually be end-to-end from chips in the clients all the way up to chips in the cloud, and they may even start pushing down into tools and fab. Okay, because these players are going to be really commodified and be trying to push up to create value. And it's on this boundary that we're going to see a lot of interesting churn. Okay, but this trend will continue, and even Microsoft purchased Nokia and got access to huge international manufacturing and distribution facilities for devices. I won't comment on chips, but Google and Apple's well known to be building lots of their own chips. There are even rumors that they were buying fab capacity. Go ahead.
I was just going to ask you, in some ways this seems like an older model. I mean, if you think back, you imagine IBM
Yep.
and all this stuff.
The pendulum swings.
So what's the significance of it? I mean, is this a consequence of the industry maturing, or why are we going back?
I think it's.
Could you repeat the question?
Sure. The question is this, things used to look this way with IBM, and then we went to a more horizontal ecosystem. I mean, IBM has always been vertical. If I go to the enterprise space, the chart would look a little bit different. This was the consumer space that was perhaps less mature. I think at a given time when you see a horizontal ecosystem or a vertical ecosystem, it's a function of both the level of investment required in a technology and the business scale, and where people are able to build the moats to preserve monetization. And so, for example, 10 years ago, Intel was able to build processors with enormous capital investment in NREs that would go to thousands of customers. The same part could proliferate across many segments of the market. And they might turn, and IBM used to do the same thing with their mainframes, and they might turn some functionality on or off or use them in different packages. But they would design a small number of parts, and they would put hundreds of millions to $1 billion into these parts. And so in 2001, I mean, sure, they had some competitors like AMD, but the thought of one of these companies trying to out Intel at its own game was crazy, right? Because how could you possibly do it better than Intel? They have their integrated process technology. They have all of this stuff. But as the gains have slowed and the need for differentiation has increased, it's now profitable perhaps for some of these companies to start investing, because the cadence is not as fast, and they're now at enough scale with some of their markets, advertising, consumer phones, distribution networks, which is really what Amazon is to first order. You have enough revenue that they can actually afford to build their own and specialize and get away from the rest of the market. So I think it's where you see these monetizable moats spring up, coupled with how much investment you can make to how many players. And the thing that's interesting about that is as it segments more, when Apple builds its own chips, it slices off a big chunk of the volume for the phone industry, so that the integrated providers now have a smaller volume to sell to. And if another company slices that off, eventually, if you have a horizontal provider and you're their only customer, right? You just acquire them and cut out the margins. So, Ross?
To what extent is it differentiation or the desire for
I'll repeat the question.
versus the need to remove abstraction layers in order to...
So the question is, to what extent is there the need for differentiation versus the need to remove abstraction layers? I would argue that there's an overlap between those two. So if you want to differentiate and you have a very stable stack on top, you might need to actually remove abstraction layers or work across, and that frees you to differentiate more quickly. I mean, if you can't change x86, there's a limited number of things you can do under the covers, but if you have the whole stack. And so as we've seen general purpose processing cap off, it's, a lot of people are arguing now for specialization, but it's hard and it's inefficient. I mean, in terms of design, no one really knows how to do it. But it's hard to do if you're a horizontal player because you don't know what to specialize. But once you have these integrated stacks, you can now specialize across many layers, and you're completely free to blow these things open. I mean, Apple has been a master at that. They've changed ISAs many times in their career because of their model. But I think we're going to see that cadence increase because everyone's competing, and now increasingly everyone can specialize and differentiate. And this is necessary for aggressive specialization to happen. Okay, so sorry for the bug on the slide, but I would argue that from an architect's perspective, from my perspective, architecture sort of is everything when you don't get process scaling gains anymore. Now, of course, from a circuit designer's perspective, you might say we still need low power circuits. And from an energy harvester researcher's perspective, you might say we need to do better energy harvesting, and those are all true, right? But we don't get free gains from the process. So if we think about architecturally, if you're not getting things from the process and you want to build something that's fairly programmable, general purpose, what do you get from the design? There's lots of options, and this is a variant of a very well-known spectrum where you have fully general systems on one end, single CPUs that are optimized for single thread performance, but they're 1,000x less efficient than ASICs or 10,000x, depending on the CPU and the ASIC. And then there's lots of points in between where you get increasingly specialized or harder to program. And here, with ASICs, you can't program them, but you get much more efficient. And so what I want to talk about a little bit for the rest of the talk is what are the architectural directions we should think about for ultra-low power computing? Or is it we just have commodity, Cortex A9 ARM cores, and they don't get much more efficient, and that's what we use? And I don't think that's the case. I think there's actually still a lot of fat left to be cut, giving us fairly general low power and highly energy efficient computing for all these very deeply embedded, ubiquitous devices and wearables and even mobile. And where should we be investing in this space? And what are the sources of the overhead that we can cut out? Okay, so if I look at the world today, and this is an architect's perspective, and I think this is complementary to better batteries and low power circuits and all of that. We have, in the phone space, we have the big little approach. So I've got some one or more high-end cores, and then I've got some small in-order ARM cores that I can offload things for doing continuous sensing and continuous monitoring. When I want to have something that's running more continuously, as opposed to run hard and stop, I put it on the little. So that's pretty common. I've got mobile GPUs for doing SIMD sorts of computations. And the value of doing SIMD is, of course, I cut out some of my front-end overhead because I can do one front-end operation and then many data operations. So I'm amortizing the overheads of my instruction fetch and decode and all that. In the lower, even lower power space, we're seeing customized cores, and Tensilica is a good example of this, especially for the DSP space, where you can start to customize specific instructions that are key to that flow. And so you might have a many core array of Tensilica parts to handle a lot of the fairly fixed functions that you want in deeply embedded devices. But of course, those can't be, you still need programmability because you might change the algorithms, but you want to get them pretty close. And then of course, on mobile phones, in other words, we have lots of ASICs. Okay, and those are being used more and more because the need for efficiency is greater. Of course, as you go down along the spectrum, you get less general, and it gets harder to design these things, and you're less agile, and that's a real tension that we have. Do you completely redesign your SoC every time you want to deploy a new device? That's very expensive and very hard. Okay, so if we start thinking about specialized accelerators, of which the ASICs are one version, I'm going to talk a little bit about the cloud for 2 slides. That's the only time I'll talk because I'm focused on devices here. But some of the constraints are similar. So one nice thing is when you have CPUs, you're fully general. You write high-level software, you can compile it down, you can run. Of course, if you want to maximize efficiency, you do ASICs, and then accelerators sit somewhere in between where you want to be perhaps domain specific, so you're general within a domain and you don't get all the efficiency, but you get some. So the accelerators sit there. And especially in the mobile space and the client space, there's something between the CPUs and the ASICs that I call the uncanny valley of death for accelerators. And this is, it's a play on the HCI concept of the uncanny valley, where things look almost lifelike but not close enough, and they're really profoundly uncomfortable. If it's a cartoon, it's fine. If it's almost human but a little bit off in the eyes, it's really creepy. Okay, we have a similar problem with accelerators, which is if we have some workload blocks that are really, really important, you're gonna do them all the time, you stick them in ASICs. And you do maybe your top 5 or your top 6 in ASICs. So in mobile phones, we have lots of ASIC blocks all over the SoC. And then your CPUs are fairly power efficient, especially if you do the big little thing. So your accelerators need to be more power efficient than the little cores. But the value proposition is that they can run a bunch of things, but you've already taken the 10 most important things off the table. And so they have to accelerate whatever's left, and the value proposition very often usually isn't high enough to justify building those in addition to the little core and the mobile GPU. Okay? And so we've actually seen this over and over and over in the phone industry, where people are pushing down some accelerator path, and it looks great until they decide to harden these 5 things, and then game over. So these are all the dead accelerators sitting at the bottom. Okay, and now in the cloud, and this is just another constraint we have, and this is related to some things on the client space, is that if you think about what you actually want for a specialized accelerator in the cloud, this is the lifetime you need it to be viable. And this is the % of servers that it needs to run in, okay? And so the reason I have 5 years here is if you're going to build an accelerator, an ASIC accelerator, something specialized to be very ultra low power for its workload, you want it to be working for about 5 years, because it's going to take you 2 years to design it, get it on the roadmap, get it into the server design, and then the server is going to be, have a lifetime of about 3 years. 2 + 3 = 5. So you want that thing to be stable and useful, even if the software and the workload mix changes. And then, of course, because of the overhead of manageability for managing large-scale data centers at scale, you really want this thing to be useful in almost 100% of your servers. Okay, so what you really want is an accelerator that sits in every server, because you don't want to specialize them so that workloads can't migrate around as demand shifts. And you want it to be viable for 5 years. So this is sort of the bar that would justify a fixed accelerator in the cloud, and this is what we actually see. Right? So any one property is not going to be running on more than 2, 3, 4% of your servers, at the scale that these large companies operate. Even the biggest single workloads, first-party workloads like search, ranking, for example, only runs on a few % of your servers, and the software is changing monthly. Okay, so it's really hard to get ahead of this. So so if this is what you want and this is what you have, it's actually really tough. Okay, so that really comes into ubiquity. You want this thing to run everywhere and be ubiquitous over space and time. And so in the cloud, we've made a very big bet, as a lot of you know, on FPGAs to try to bridge that gap. But that doesn't really work for the mobile space. Some phones have had very small FPGAs in it, but the FPGAs, since it's spatial parallelism, you tend to need a lot of silicon real estate to do interesting workloads, and that high silicon real estate is too expensive for these small mobile devices. Okay, so in the data center, we dealt with this by building this fabric where you can offload services, and you've probably heard some about that in this in this faculty summit. But this doesn't really solve the problem in the mobile space. So I think we have the cloud story pretty well in hand. But what are we going to do about the client? And by client, I mean even smaller devices or wearables or deeply embedded devices. So when I was thinking about this after G invited me to give this talk, and I'm trying to think about general computing, so programmable devices, not ASICs, because those, we know how to do those. They're just hard and expensive. There are really 4 targets. And Mark next door, thank you all, by the way, for coming to my talk. So we didn't have 100% of people in one room and 0% in the other, although you might have been better served to go next door. Mark is actually talking about this today, so I'm stealing a little bit of his content, so you're not bereft. And really, there's four areas where we see opportunities to harvest energy. And I think the architects in this space, and maybe many others of you will say this is obvious and well known, and that's fine. We'll get into some more specifics. So the first is the front end. When you're fetching an instruction and decoding it and then dispatching it to issue logic, that actually takes a fair amount of energy. You're hitting instruction caches. It's pure overhead. The really nice thing it makes you fully general. GPUs use their SIMD model and the warps and NVIDIA parlance to amortize this and cut this way down. And as long as you're doing the same operation many times on different pieces of data close enough together, you can amortize some of that. But there's actually a lot of overhead here and a lot of opportunity to remove it. Computations are often very regular. Code is reused. Instruction locality is high. So how do we map things to get rid of that front-end logic? Out-of-order issue logic is the second one. Out-of-order cores are much less energy efficient than in-order cores, but they provide a very nice performance boost, and that's one reason they're still widely used, even in the mobile space. So you have big, little, you tend to have out-of-order, in-order, at least for higher-end devices in the phone space. But this is a real opportunity. If you can get rid of this, but get the benefits, you've saved a lot of energy and gotten a lot more performance. Run hard and stop becomes a lot more attractive then. Okay, then fixed ALUs is another source of overhead. You provide some set of arithmetic units, but there's a lot of times that there's other operations where you could fuse them, and you'd actually save a fair amount of energy. And this includes both the network connecting them as well as the ALU operations themselves. And then data movement is a really big one. Okay, so this is not just going out to DRAM, which is hugely expensive, but even touching your L1 caches and going through your cache hierarchy and your load store queues and all of that. So these are 4 fat targets, and if we can get rid of these or cut them way down, we can get much more energy efficient computing for more and more deeply embedded devices. Okay, so number 1 through 3, we've had a project running in MSR for some time called E2, using an edge architecture, which is built on some of the work that I did at UT. This stuff takes a long time, and so to really get the right abstractions and the right targets, what we found is that we're actually able to significantly reduce the energy of 1 through 3, even below what you'd be able to do on a simple lightweight in-order ARM core. And so this has become our primary strategy for greatly reducing energy for deeply embedded or ultra-low power devices while still getting reasonable performance in a programmable way. Obviously, if you can do ASICs, that makes sense to do. And so I'll talk a little bit about how we reduce these chunks of energy, and I'll talk a little bit more about opportunities to reduce data movement. And then the nice thing about the architecture that we've I think matured fairly well now is that it's also very extensible to specialized architectures. So it's not just fully general, but if you say, hey, I have something a little bit more custom I want to push on, it allows specialization in a fairly automated fashion. And we have a full tool chain built to support this. Okay, so the architects in here know I've been working on this stuff for a long time, but we're now getting very, very good results. And so with apologies for the people that have seen this many times before, if you have edge stands for explicit data graph execution, and there are really 2 key components in an edge architecture that are different from RISC or CISC. The first is that we take blocks of instructions and we treat them as an atomic unit. So they might be fetched atomically. They may execute in some data flow obeying order, but then committed as an atomic unit. So it's really like a programmer invisible transaction. And then within those blocks, we actually build an explicit data flow graph where instructions point to succeeding instructions. So when I was briefing some of our executives on this not too long ago, Chi-Lu asked a really good question, which is, you're getting something for free here, I don't get it. What are you really giving up? Because nothing is free, right? And it really was a great question, and it got me thinking. And that what really the trade-off we're making is, in the modern era, energy is a critical resource, and code size used to be really driving almost all of your architectural decisions. So if you go back to when CISC architectures were defined in the late 50s and early 60s, memory was so expensive that they did every single possible bit of encoding to reduce your code size and minimize that. And then more recently, you know, in the 70s and early 80s, when the RISC architectures were being defined, the goal there was to reduce the control logic so you could actually fit the whole thing on one chip. Okay. Now, there were other benefits like easy pipelinability that came later, ability to have fewer instructions so that the compiler could schedule them, but that was really designed to drive down the microcoded control. And the RISC designs were able to be integrated onto single chips first. You know, so in some sense, both of those were storage-efficient architectures. One was instruction encoding and one was control logic. And that what we've actually done is taken an opposite approach, which is to say, we're actually going to increase the code size and bloat the binaries by 30%, and in some cases as much by 50%. And in deeply, deeply embedded devices where you still have tiny amounts of memory, this can certainly be a problem. But in the phone and wearable space, we think it's actually an appropriate trade-off. And so what you do with that bloating is you're actually conveying a lot more information from the compiler that allows you to save energy at runtime. You know, so an out-of-order core will discover all of these relationships between instructions dynamically using expensive hardware. We're actually doing that analysis. Well, the compiler already knows that, but conveying it through the ISA to the hardware. And the cost is an increased binary size. The benefits are that you can run efficiently with much, much less energy. And so I'll show you how we tackle those three things. So just to get us all on the same page with the various overheads, so what an out-of-order core does, and I think most of you know this, so I'll be quick. This is your list of dynamic instructions, your dynamic instruction order that gets executed in, say, a RISC ISA. And you'll be fetching some number of them at a time, let's say 4. So you fetch 4, you fetch another 4, you fetch another 4. And then you start doing register renaming to identify the dependencies among instructions. And register renaming requires a fair amount of analysis, and you have to save the rename maps to roll back in case of a branch misprediction. Okay, so you're doing all of this analysis, and then building this graph, which you're maintaining at runtime in the hardware. And then, of course, so as you're fetching instructions, you're adding new instructions to the graph, you're connecting them with your register renaming, and then you're taking them off the top with commit, and you have a window rolling down over the program, maintaining the fraction, the data flow graph for the fraction of the program that's in the window. And then when you actually want an issue instruction, you take the tag associated with that instruction and you broadcast it to a fairly hefty cam, and that cam grows very rapidly with issue width, and that's how you actually traverse one of these arcs. You take a tab, you broadcast it to a cam, so you're broadcasting it to multiple operands for all of these instructions, and then I2 and I4 will say, yep, we're the ones that need this, the outputs of I0 and I1, and now you're traversing that arc, and now, if it's other input dependencies are satisfied, you can issue I2. So all of that overhead of renaming to form the arcs, cam broadcast to remove the arc, or to traverse the arc, is runtime overhead to rediscover stuff that's largely known by the compiler. Not completely, because you don't know what control flow path is going to be taken. And then, of course, when instructions commit, they're removed from the graph, and like I said, this is a rolling window on a fraction of the program's dynamic instructions. Okay. And so as an alternative, what we actually do in an edge ISA is we actually build this graph a priori and expose that through the instruction set. And so here I have 3 basic blocks, so I have a branch here that's jumping here conditionally, so I might fall through and go here and then go to here. And you can see that we've got these, here's the graph that's built. And this, the overhead's a little higher here, of course, because it's a small example. But I have the same graph here where instructions now, like let's say this add, which corresponds to this add here, rather than having 2 input source registers, R2 and R3, that write the result into R1, this add is getting sent its inputs from somewhere. Actually, it's getting sent its inputs from this register read and this register read. So these reads go and pull operands out of the register file and send them to this instruction, I5. It will receive these 2 operands, it will fire, and then it will send its results explicitly to I8 and IC. Okay? And so this whole graph that previously in an out-of-order core we had to build dynamically in hardware, we actually encode in the compiler through the ISA and just hand it off to the compiler in one chunk. Okay? Again, this is not new stuff that we've been working on this a long time. But now in a microarchitecture, you have your caches, fairly, I mean, this is a fairly standard thing. Now you have an instruction window, but rather than a centralized register file, you have one for the begin and exit to a block. We can actually, you now have buffers to hold the operands that are being produced for each instruction. And so an instruction issues and it has a pointer to say this buffer slot and this buffer slot, and it will just write the results in there and there. Okay? And I don't have time to go into this in great detail. There's lots of stuff to read if you're interested. But one of the really nice things is that when you have any recurrence in the program, okay, and so if you have a streaming app or you have a loop, and some enormous fraction of many programs is actually just in recurring loops, this data flow graph in a block that's been mapped to part of the window, of course you can map multiple blocks, is actually resident there. And the way you can re-execute that loop is simply by clearing the valid bits for that block, and then a number of the independent instructions like the reads will reissue, go to the register file, and you'll start traversing that graph again. So since that graph is pre-constructed, you don't need to change anything. You can just sort of reinitiate it. And now if I have a loop that's consisting of multiple blocks, 1, 2, 3, 4, for example, and I can fit it in the window, I can hold it there too. And as each block finishes, it will just refresh. And so what you've done with that is you've actually cut out all of the front end. You're no longer fetching, decoding, dispatching instructions. All that energy is gone. So while you're in that loop mode, the only energy you're expending, aside from leakage, is issuing instructions. So you have instruction select and wake up, running them the ALUs and forwarding them back. Okay, you still have data movement, you still have the memory system, okay, but you've actually cut out that front end logic. And then as you provide more and more of these resources in a larger and larger fabric, you can actually capture the working set of larger and larger recurrences. So perhaps an inner loop and an outer loop. Okay, so this is a first step towards actually spatially mapping large regions of code and just being able to keep going and refreshing them. And this is similar in spirit to what PipeWrench tried to do at a much finer granularity. But pinning the code and being able to refresh without refetching when you have something that maps well is really, really nice. Okay, and then as the architects here know well, we actually put the support in to be able to dispatch different blocks to different, from one thread onto multiple cores. So if you have an 8-core array here, you can of course run 8 separate threads, which when you have the threads gives you good energy efficiency because each one is running on a very energy efficient core, especially when you're recurring. So each of these cores has already cut out all of that energy overhead for out of order execution, with the exception of the wake up and select logic. And then when you're in a recurrence, all of the energy overhead for doing the front end, fetch and decode. But now, what you can also do is fuse cores and dispatch blocks, different blocks to different cores, and treat those multiple cores as a single fused entity. So I can run one thread on 4 cores and say, for example, 2 threads on 2 cores each. And that allows me to have a larger spatial mapping for doing these recurrences. So in some sense, I could say, hey, I want to allocate 5 cores because that's enough to fill up this loop that I have. And now I can cut out the front end energy. It also allows me, though, to dynamically shift between big, medium, and little, depending on the needs of the workload. Okay, so I can be running some number of cores just doing continuous sensor processing and analysis to say, hey, is there something I should be paying attention here to? And those are typically loops. So I can just be sitting issuing instructions, and I can dial down the clock rate just to be able to ingest that input data fast enough. And then when something interesting happens, I can actually spin up, fuse all the cores, and then run at it very hard. And this is a very high performance but also energy efficient substrate. This would be a 16 wide issue sort of mega core. So I don't want to spend much more time on this, but so if you think about this block atomic execution model that we've been working on for a long time and are now, I think, making very, very good headway in the energy efficient space. So the intra-block data flow exposed through the ISA gets rid of most of your out-of-order energy. So you can actually get higher performance, much higher performance than an in-order core for similar levels of energy. You can pin the blocks in the processor core to cut out your front-end energy. You can now issue blocks to more than one core, allowing yourselves to sort of grab more or less energy depending on your workload mix and the needs of your system at the time. And then finally, these blocks also form, they can run from 4 to 128 instructions. They actually form an interesting configuration that you can use to synthesize into an accelerator. So if you have a block that's something that's very common, that you're going to be doing a lot, let's say in your phone, you're processing some sensor stream and it's in a block or two, what you can actually do is take that block and synthesize it into an ASIC, but have the same interface that you would have to software. And so when the software reaches that block, it can go out to the synthesized unit. And this provides you an automated way to take code regions and synthesize them into specialized accelerators. And then in the next generation, if you deprioritize that piece of code and prioritize something else, you actually go and turn this one back into software in the sense that you'll just run it in code and synthesize the next one. So you can kind of move back and forth automatically in different implementations between hardware and software. And as kernels get pinned, it gets much more efficient. Now, in terms of data movement, which, as you remember, was the fourth. Ross, go ahead.
About out of orderness, how global is your out of orderness? One block, multiple blocks?
It's actually global. It's across as many blocks as you have in the window. OK. Now, that being said, so sorry, the question was, how global is your out of orderness? That's actually an implementation choice, because you could decide to save energy to enforce sequential instruction semantics between blocks and run blocks in order. Or you might map a bunch of them and then pre-issue the loads, but then wait until the last block was finished before moving on to the next. That would actually simplify some of the logic at the load store queue interface and save you some energy. So that's really a policy decision. But in general, I think if you want a big window and to get that latency tolerance, we don't actually add a lot of energy overhead to do that. There's some at the load store queue. That actually buys you a fair amount of performance. If you just want to run blocks sequentially, you would want a much smaller core that only runs one block at a time.
So you need to do some renaming, right, of those edges?
And then you have to do renaming between the register edges. I mean, any intra-block values, so the question was, you need to do renaming between blocks, and that's absolutely right. Any inter-block operands or data flow arcs, whether they're through registers or through memory, need to be treated the same way they are in a conventional out-of-order core, with some associative logic. The good news is that that number is actually much smaller than you'll typically see, because if you have a block of 64 instructions, there aren't that many temporaries going from one to the other. So you don't get rid of it, but you take it down by a significant fraction. That's a great question. Thank you. So in terms of data movement, now we think about how on a silicon substrate that we want to be highly energy efficient, we can make things more efficient. So we all know that you can block things, and that's actually very useful. This is what Mark is talking about next door as a way to try to block things for synthesizing accelerators more automatically. Certainly you can stream things through, and the idea that you lay out a series of kernels and then one forwards directly to another. There's been a lot of this at Berkeley and Stanford and MIT and other places over the years. Stream it, things like that. Systolic arrays are a very synchronous special case of that, where you're mapping out graphs of accelerators that communicate point to point. Joel Emmer and his group had a really nice paper last year called Triggered Instructions that tries to take a tiled architecture and turn it into and have that sort of streaming behavior, where tiles, have generalized instruction graphs which are a little bit like ours, and they will send, operands through FIFOs directly to other tiles, bypassing the caches. And they showed an order of magnitude increase in efficiency over fairly efficient cores by doing that. And then, of course, you can tackle this technologically, like bringing DRAM in package. And there's a lot of work going on there that I think is going to take off. I mean, we're definitely looking at in-package DRAM. And right now, if you think about, there's two, you can say milliwatts per megabytes per second or picojoules per bit. How much energy does it take to support a given rate of bandwidth? We tend to think in milliwatts per megabytes per second. DDR3 is several hundred. 300 to 400, and 40 is sort of the limit bounded by the energy to just access the DRAM row. But there are solutions that are bringing it down to 120 and 80 by putting it in package, and they look very, very efficient. So that'll help a lot. And of course, you can eliminate memory accesses with techniques like the streaming people do with triggered instructions. So we expect to see those come down, but that's the fourth category of fat we're working very hard to cut out. And then as an example, going back to the cloud, in our Bing accelerator that we built on our FPGA fabric, in the front end of the pipeline extracts features from a document, and there are thousands of features that you extract. And so to make this very energy efficient and high performance on an FPGA, what we did is we just built this large array of finite state machines, each one of which extracts a feature of families. You have a document coming in over PCIe, and then we actually turn that into a stream of tokens. That's just a conversion. And then we broadcast that stream of tokens to every of these FSMs in parallel, and they're all in parallel extracting their features from that flow. So this is an example of one of these graphs of kernels where there's no explicit data dependence from one to the other. It's just a broadcast network. But it's one topology, and you can do many other things like this. And this saves enormous energy because you're only doing the data movement once and extracting thousands of features, where in software, you're just doing it over and over and over again. So even though the CPU is less efficient to begin with, you're doing much more computation. Okay, and I'm out of time, so I was going to talk a little bit about how, some of you saw Hadi's talk, but by adding a little bit of error and approximation, you can actually then do algorithmic transformations on the program. And the recent work we've done on NPUs will transform a general code segment into a neural network, and that allows you to run it takes diverse code and then transforms it into a fixed representation, i.e. a neural network, that you can run on accelerators, and we see very large energy efficiency gains by doing that. So this is the range of applications that we transformed in the paper, and it's fairly diverse. And the results in terms of the quality of the output were good in all of the cases. That the perception didn't say this is much worse than this. And then when we did a digital version, which was in Micro 2012, we saw 6.9 times energy delay gain. And then in ISCA this year, we had an analog neurons and mixed signal circuit that actually bumped that up to about a 23x energy delay gain. And so I think this is another good way to think about, for ultra low power, can you actually transform the code into something that will run well on an accelerator that might not be general purpose, but which will be much more energy efficient. And the NPU actually has a lot of the characteristics that we talked about earlier. That eliminates all of the front end code, because you're turning a code stream into a fixed invocation of a neural network where the network is already embedded on the hardware. So you get rid of most of the instruction fetch and decode energy. The out of order energy is sort of gone because you have a highly parallel thing. So you don't need out of order issue to get good parallelism. And so it cuts out several of those. And the data movement is largely local. So it makes that pretty efficient. Okay, so I think given what's happening with Moore's law and what we're going to get out of the process, which is basically nothing, we're going to need much more efficient execution. And we see as you all know very well, we see tremendous pressure in the wearables and sensor spaces. We just need enormous amounts more energy efficiency to do the sorts of things that we want to do, especially in wearables. But we're not going to get much more for process scaling. And if you're willing to run very slow, because there's a lot of stuff you can do like near threshold computing. But in a lot of the cases, we need much more performance. Okay, so I think in addition to all the good work going on in energy harvesting and circuits, we need much more efficient architectures that are still somewhat programmable. And of course, there'll continue to be a lot of ASIC work, and I expect that will increase as the tools get better. But that's expensive and slow, and things change. So we still need programmable things. And then I said here the holy grail is programmable. CGRAs means is more like coarse grain reconfigurable architectures or hardened ALUs with some configurable fabric. And those haven't really taken off. They're really hard. No one has really nailed that yet. But many of the things that I was describing, the triggered instructions, the stuff we're doing with E2, they have a CGRA-like feel. And the goal is really, can you get it down so what you're really just doing is running code at high performance with good utilization of your ALUs, but just beating through these ALUs and spending the energy there rather than all of the bookkeeping logic, the control logic, the front-end logic. And so I think whoever really nails this is going to have a great, great run in this deeply embedded, ultra-efficient energy space. And we're taking one crack at it. Other people's are taking others. And so the two directions we've really looked at are E2 and neural transformation. So that's my talk. Thank you very much for attending. I'm happy to take a few questions.
A couple of quick questions.
Yep, David?
So do you see a time
Or 14.
14.
Yeah.
Where the cost of ASICs goes down quite a lot, and the economics of building ASICs and mask sets and things like that is very different from what it is now.
I think that's exactly what the question was. Do we see a time when we're at that last node where the cost of ASIC gets reduced over time? I think that's exactly what we'll see. It'll be a commodity, and the tools will just get better and better. The companies that support doing that will proliferate. But it will be slow, right? It's really hard. The design rules are growing exponentially, as you know, right? So we have to turn that around and bring them down, or at least find a way to hide them. So we'll just see a slow declination over time. And so 10 years from now, it will be much better than it is today. Every year, it will probably get a little bit better, but it's not going to be a fast,
Quick follow-up. Does that mean more chip startups will be birthed in the future?
I think we're at a nadir, and I think once that technology stabilizes and people are really desperate for performance, I think architecture will see a renaissance because we have to do things different. And so a lot of things that were previously unthinkable or unnatural will become natural and thinkable. And I think you'll start to see more ASIC startups coming back. In fact, I'm already starting to see that move a little bit. So, yeah, Brandon?
I really like your holy grail on the last slide there. I think the key word in the holy grail that you listed is programmability.
Yep.
What you talked about throughout the course of your whole talk is taking those four things and trying to change them in pretty fundamental ways. So I guess I want your opinion on whether we can get away with keeping the programming abstractions at the kind of highest level end-to-end programmer the same as they are now, or do you think that there are going to be fundamental changes in the way that programmers have to think about writing software to make all this stuff that you talked about work?
So the question was, and it's a great question, will we have to change the programming models to exploit these new architectures that will come to mine out those things that I talked about as sources of overhead? I think what you'll see is a little bit of both. So there's already a lot of work in domain-specific areas, and we see it in Catapult, you see it elsewhere, where there's a class of things that you're interested in, and you're willing to have a more restricted language or a special language, and those will proliferate. I don't think there's any question about that. I think that as the language community doesn't, for obvious reasons, doesn't like to target weird architectures that aren't in widespread use, just like the architecture community really doesn't like to plan on devices that aren't really ready for prime time yet. I mean, people write papers, but you don't know what's going to happen. So I think we're likely to see that happen come from the bottom up. We'll come up with new architectures. We'll program them by hand and twist and turn and contort to be as productive as possible. And then that will go up to the compiler and eventually the language. And the languages may shift a little bit. Right? I don't think we'll be jumping to radical languages that look nothing like we have today. I think we'll be looking to keep the model fairly similar. But we may evolve away. And I don't know, we might take a big step function to functional languages, the only way of doing this. But I would be surprised if that happened.
A quick follow-up to that is you're talking about a lot of kind of accelerators and combinations of accelerators and CPUs and things like that. Do you think that, I just want your opinion on this
Sure.
as well, this is a really important question. Do you think it's reasonable to have one uniform programming abstraction for all these different kinds of devices? Or do you think going forward we may have a more fragmented way that we build systems with some glue stuff that puts pieces built differently together?
All right, the question is, are we going to have a clean abstraction or a mess? I think we're going to start with a mess, and we're going to just work to evolve it to be clean over time. I mean, one reason I've been willing to stick with the E2 stuff for so long is I see lots of ways that we could take many different programming models and actually map them onto the same substrate. So I think we could actually, rather than having a heterogeneous mess, you actually have a fairly homogeneous substrate that does pretty well on most of the things. So I've been willing to continue that investment because I think that would be really good if we can pull it off. But we don't know. But I think initially, like what we see in Catapult as we're building a lot of these services, is you're doing a lot of it by hand. You're grabbing different things. It's kind of a mess, and you're just trying to get through it. And then we want to evolve towards cleaner models. So we're in for a messy time, no question. Yep.
Doug, this was a fascinating talk for me because
Thank you.
in coming from EE community, we have been dealing with synthesis and custom acceleration for a very long time.
That's right.
And we always, I think after 2 decades of work, always came down to this question about what's the right programming model, and we somehow have bad
Yep.
spent.
Yep.
And of course, the major highlight was that the ALU was like 4 picojoule per op or something.
Tiny.
like that.
Yep.
And the register transfer was like 100 plus picojoule. So it basically came down to data movement.
Yes.
And then it punted the problem to famous one-element bottleneck. So the question I'm coming to now is, if you were to take a longitudinal perspective with what you have done in E2 and maybe even with Catapult, what are the topmost architectural lessons that one could take home? One, of course, is reducing the front end, which I think is new, which I'm able to see now. But then there is parallelism now at a much worse level, simply because there are multiple cores or multiple CPUs.
Right.
So how do you see that coming together? Do you see, is there a role for customized accelerators?
So there's a role for customizing. Let me summarize the question. What are the general lessons we learned from the client and cloud work? If I could put a short version of it, and just for the camera. So for the client work, I think the rule is that programs are intrinsically data flow graphs with uncertainty about edges. And we do a very poor job in mapping those out efficiently. And I don't just mean within one of our instruction blocks, I mean across a substrate. And of course, there's recurrences. And so, but data flow graphs also capture instruction movement. Joel Emmer's recent work is a really different take on how to manage those graphs. When you can contain a whole kernel within the silicon, when the whole thing is mapped, so you don't need to do cache misses, right? And so I think I think the general rule is we should be thinking about these things as graphs and how to lay out the graphs on hardware that's as homogeneous as possible. And we might have to give up on some of our programming model abstractions. Like, do you want, like Taras's question, do you want out of order across blocks? So by weakening or strengthening those, you can make your hardware more or less complex. But we really want to think about substrates that can map graphs to minimize all the overheads as well as data movement. Okay. I mean, we haven't gone very far into the data movement and explicit communication between load and store space. That's something that Joel jumped out ahead on, and we're thinking very hard about. On the Catapult side, on the cloud, I think the project's still too young to have any strong conclusions. I mean, parallelism is good, reuse is good, data movement's bad. I mean, it's kind of the obvious stuff, but I don't think, you might ask Andrew or Eric or Adrian or others on my team, but I don't have yet we're still building the services and it's still early and the architecture is shifting very fast.
Let me just add one comment. So we would have these kind of discussions on efficiency and synthesis and come to the conclusion always, invariably, that the stack depth was the cost of the overhead, the abstraction stack from
Yep.
to so on. So how would you fund and compress that to make it more efficiently? And
Can I answer that then?
yeah.
Okay, so I think you do two things. You try to provide a more efficient architecture without changing the stack too much. That's your ante, right? That's what gets you in the door. But then you want to provide a bunch of opportunities so that people can mine out more efficiency by then disrupting the stack all the way up. And so that's exactly the strategy we've taken with the client work. Let's try to make things more efficient, but not really mess up the stack. But then now I see all these opportunities for doing direct, producer-consumer communication, mapping whole kernels and pinning them, things like that. And that will change the stack, but we haven't pushed down very far because I don't think we've gotten the buy-in to the point that I'd like it.
Yeah, the second part of my comment was that one community that has been very successful in compressing the stack of abstraction for performance reason has been network.
Yep.
And so, I think 4 or 5 years ago, this project that I ran in which we took the coprocessor and put it as a network interface.
Mm-hmm.
So the abstraction was as a network interface. And it turns out that can give you a lot of acceleration advantages. We were not doing efficiency at that time.
Right.
Okay.
Thank you. Thank you for the comment.
Thanks.
Thank you.